here in this lecture we will learn about the strain energy due to bending, and we will know how much strain energy is getting stored in a beam while it is under bending moment. So if we consider this is a beam, and if we take two sections at a distance of dx, and we take an elemental cylindrical element which is having an cross-sectional area dA. So we are taking an elemental cylinder which is at a distance of small y from the neutral axis, and its area is dA. So we are taking elemental cylinder which is at a distance of y from the neutral axis, and its area is dA. Okay, now because this dx is very small, so that's why we can consider that the bending moment in this region is kept constant. Okay, let sigma be the bending stress. Now if that happens, then the strain energy in the elemental cylinder is, we know the formula, sigma square by 2E into volume. Okay, so when I put the value of the volume will be equal to dA, its area, into dx, its length. Okay, now if we consider the strain energy stored in the length dx, then if it called del u, then it will be integration of sigma square by 2e into dA into dx. Now if we put the values of this sigma is bending stress, so it becomes m by I into y, okay, into dA into dx. Now m we have taken constant, so m square, dx, the length is fixed, so dx is a constant and comes out by 2ei square. Okay, e is single and I is square here. Now in integration y square dA. Now we know that this y square dA is basically I. Okay, so I means moment of inertia. So if we put the value, then what we get is this y square dA is equal to I. So it will be like this, m square dx by 2ei, but this is for only length dx. Now for the whole beam, if we consider the whole beam, then the strain energy stored in the whole beam will be equal to integration of m square dx by 2ei, and the limit of the integration will be from 0 to L. If the length of the beam is L, then it will be from 0 to L m square dx by 2ei. Okay, now this is the strain energy that will be going to be stored inside this beam.